Hello, this is the first homework set of problems on the basic skills unit for the data evaluation. So we're going to go through here. There are a couple of problems and I'm just going to work them through and show you how they're done. So this first problem here, it says we've got a farmer, he's trying out a new sort of feed used to raise cows, and he's adding scoops of this new feed to the cow's normal diet and observing how their weight changes. And so we're going to do a data evaluation on that. So the first thing we've got to do is we've got to set up our graph. It says that we want number of scoops on the x-axis, and we want the weight on the y-axis. So that is what we'll do. On the x-axis, it goes to 10. And so each box there, if we're talking about the x-axis, if it's going to go to 10, we say 10 boxes divided by the 10 scoops divided by the 20 boxes that we have there. Each box is going to equal 0.5. All right, so when we label this on the x-axis, we're just going to have, we'll skip every other one, but it'd start out here 0, and then it'd be 0.5, and then 1, and then 1.5, and then 2, and then 2.5, and then 3. All right, all the way through. Going on the y-axis for the scaling, we've got 1350 there. You could scale it up to 1400, or you could scale it up to 1500. I don't really have a huge preference there, but I think that 1500 is slightly nicer, so I think I'll go ahead and do that. So what I'll do is I'll say 1500 divided by 20 boxes is going to give me 75 for each box. And so then what we have there is we start out here at 0 again. The first box is 75. We skip that one. We'll label at 150. Next box would be 225. We'll skip that one. We label at 300, and so on all the way up. So I'm going to go ahead and finish labeling these and plot the points and put the line of best fit on there, and then we'll go from there. All right, so there that is. Next we need to find a couple of points on here to do our slope with. So just looking here by inspection, that looks like it's at a nice intersection. And then up here, this one looks like it's at a nice intersection, so I'll use those 2 points. The first one is at 1.5, 1050. The second one is at 8.5, 1275. All right, doing the rise over run there then. $10.50 to $12.75 is 225. All right, going 1.5 to 8.5, that is a change of 7. Which gives us a slope of 32.1, and the units on that would be pounds per scoop. All right. An explanation for what this would mean would be that for every additional scoop you use, the cow's weight goes up by 32.1 pounds. Going on to the back here, it says determine the vertical intercept and its units, and then provide an explanation for what the vertical intercept is. So if we look back here at our graph, vertical intercept is where it intersects there. It's just above 1,000, it looks like. So I'd call it probably just around 1,000. So I would say 1,000, and it's on the vertical intercept, so that is 1,000 pounds. All right, and then what does this mean? This is the weight of a cow if you don't use any scoops, or just the normal weight of a cow before any of the special food is given. Now, writing this into a formula, we need to use the slope that we got on the other page, which is 32.1 All right, and this 1,000 for our y-intercept, we start with y equals mx plus b. All right, then we put in the things here that we have. So w, weight is our y variable, equals the slope was 32.1 times the x, which is the number of scoops. I'll use n for this because I think s is kind of a bad variable to use. It ends up looking like a 5 too often. So plus 1,000. Okay, oops, 1,000. And then in this case, W equals the weight in pounds. And N equals the number of scoops. Alrighty, going on to G, it says, use your equation and show your work to predict the cow's weight if 14 scoops of the new feed were used. So we'll just plug in 14 for the number of scoops. So we've got W equals 32.1 times 14 plus 1,000. Oops. Totally messed that up. Plus 1,000. Alrighty. So go ahead and calculate that here really quick. This next one here says if you were trying to raise a cow that weighed approximately 1150 pounds, how many scoops of feed would you use? So in this case, we've just given you weight. So we'll put that in for W. 1150 equals 32.1 times our number of scoops plus 1,000. So we'll subtract 1,000 from both sides and divide by 32.1. And I get N equals 4.7 scoops. Now here you might say 5 scoops would make more sense because that's, you know, an even number of scoops. Or you could say like you would put in 4 scoops and then most of a 5th scoop to try and get it if you're trying to get exactly on, you know, 1150 pounds. So however you want to interpret that, but that's how that goes. What would your graph look like if you used a breed of cow with a lower average rate initially, but which had a larger increase in weight per scoop of food used? And so lower average weight initially tells you you'd have a lower vertical intercept, but larger increase of weight per scoop of food means that the slope would be higher. Alrighty, now moving on to problem number 2. This one here about the same farmer again. This time she's looking at some chickens. She's found that there's some groundwater poisoning that's going on here and some levels of a toxin in her chicken's water, and she's seeing how that affects the amount of time it takes for eggs to hatch. And so again, the first thing that we're going to do is we just need to plot the data, so we need to figure out our scales here. It says that milligrams is going to go on the x-axis, and the time here, the number of days, is going to go on the y-axis. So for our toxicity levels, that goes up to 20. So that's really, really nice numbers. All right, on our x-axis here, it has to go up to 20. We have 20 boxes, so that just means each box is 1. So going with our normal pattern here, this is 0, then we'll label skip a box, so that's 1, and then skip that box, we get 2, and then skip that box, and we get 4, and then skip the next box, and we get 6, etc., etc., etc. On the vertical axis, we've got 30 is the highest thing that we need to go to, so we say 30 divided by our 20 boxes, and we get 1.5, so each box is 1.5. Starting out here, we have 0, and then 1.5 is the first box, but we're skipping that, so then 3, and then 4.5, and then 6, and then 7.5, and then 9, etc., 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 all the way up. So I'll go ahead and finish that up and plot our data and find the line of best fit and then come back. All right, so I've plotted all of that out, and I've isolated a couple points here that look like points where it hits right on intersections, and so we'll use those here for calculating the slope next. So it looks like our 2 points here, that is 7, 25.5 is 1 point. And then the other point is 20, 30. All right, so then the next thing we need to do is rise over run. So the rise here, it looks like it went up by 4.5. And the run is 13. So go ahead and calculate what that is. I get 0.35. And then y units over x units, that is days per milligram. All right, and a good interpretation for this, 0.35 days per milligram, what this says is for every increase in 1 milligram that we have of toxicity, we have an additional 0.35 days of hatching time. All right. Alrighty, here, next we're going to be talking about the vertical intercept, so looking back up at our graph and seeing where it intersects there. So we've got 21, and then the line above that would be 22.5, and then it's even a little bit larger than that, so like 23, it looks like. So 23, and it's on our time axis, so it should be in days. So 23 days is what we get here. And think about that, that's 23 days if 0 grams of toxin are present. And so what this would be sort of the normal time for an egg to hatch for these chickens with no toxins at all. All right, so we've got to write an equation here then. The y variable is the time to hatch. So I'll make that t equals the slope, that was 0.35. Times the toxicity level, I'll make that capital T, all right, plus the intercept plus 23, all right, and then this one, important that I make a key here since they're both T's, the lowercase t equals the time to hatch in days. And the big T is equal to the toxicity levels. And this is in milligrams. Technically milligrams per gallon of water, but since we just said milligrams in the data table, it should be known that this is talking about milligrams per gallons of water just based on the context of the problem. So toxicity levels in milligrams. Use the equation to predict how long it would take for eggs to hatch if 30 milligrams of toxin per gallon of groundwater were found. Okay, so now we've got 30 milligrams. That's the capital T. So we're looking for lowercase t here. T equals 0.35 times 30 plus 23. Going through and calculating that, I get 33.5 days. All right, on the challenge questions here, it says use any feasible method to determine how long it would take for eggs to hatch if only 2 milligrams of toxin per gallon of water were present. So what I'm going to do here, I always think the easiest thing to do is just to look back at the graph, and so that's what I'm going to do. We'll look and see 2 milligrams on the graph, how long that would take. So finding that here, milligrams are on the bottom. We just trace this up. Figure out it intersects here, trace this over, and I get what looks like 24 days approximately. So by inspecting the graph, we get something like 24 days. H, what would the graph look like if the toxin were more potent, i.e. there was a bigger effect in the number of days to hatch per milligram of toxin? So in this case, we're talking about the slope of the graph again. It doesn't say anything about the y-intersect being changed, so the slope here would be steeper. All right, and that is that. So if after watching both videos on the problems that we did in class and on this set of homework problems you're still confused about these, make sure you talk to me and we'll try and get you sorted out before the quiz. You know, I'm always welcoming students to come in and talk with me, and I hope you'll take me up on that if you're still confused.